From its perch a million miles beyond Earth, the James Webb Space Telescope will glimpse the dawn of time like nothing before it.
The James Webb Space Telescope has quickly become a game changer in our pursuit of celestial truths, reshaping our understanding of the universe itself. Since its launch, Webb has pierced deeper into the cosmos than ever before, uncovering the secrets of the earliest galaxies and the atmospheric compositions of distant exoplanets. Recently, it has revealed extraordinary phenomena that defy categorization, ghostly objects that are neither planets nor stars. Meanwhile, an unpredictable, expanding universe dances tantalizingly just out of reach, much like the mind-bending adventures in Interstellar. Unclassifiable objects in the Flame Nebula.
We're looking for some of the faintest objects that there are to see in the universe. In fact, we are looking for the faintest objects.
In the Flame Nebula, a bright star-forming region in the Orion constellation, astronomers using the Webb Space Telescope uncovered a curious population of objects that blur the line between planets and stars. These entities, known as brown dwarfs, are too small to sustain nuclear fusion like stars, but more massive than the gas giants in our own solar system. For decades, brown dwarfs have eluded astronomers due to their faint infrared signatures. Now, thanks to Webb's powerful infrared capabilities, researchers have begun to detect them in greater detail and larger numbers than ever before. What makes this particular finding so compelling is not just the presence of brown dwarfs, but their surprising properties. Several were found roaming freely in space, unbound to any parent star or planetary system. Some are as small as 2 to 3 times the mass of Jupiter. This discovery raises new questions about how such objects form. If they're not the byproduct of traditional star formation, could they be failed planets or something else entirely? For the first time, Webb has probed below the mass limit where astronomers thought such objects could exist, pushing the boundary of known cosmic structures. According to astronomer Michael Meyer, Webb has even uncovered evidence that challenges earlier assumptions about mass thresholds for free-floating objects. If brown dwarfs can be this small and solitary, then the line between planet and star becomes even murkier. Meyer noted, quote, "If that limit is real, there really shouldn't be any one Jupiter mass objects free-floating out in our Milky Way galaxy unless they were formed as planets and then ejected out of a planetary system." This breakthrough suggests a dynamic and sometimes chaotic process of celestial evolution. Planets might not always stay bound to their stars, and some objects in the universe may be wandering vagabonds, born into chaos and surviving in isolation. The Super Venus discovery and a new planetary category.
Take Neptune, shrink it down by about a factor of 1.5 to 2, and that is maybe what this planet is. In that case, there would be this deep, there's no real surface, right? You can just fall all the way down. There's no real land.
Because it's gaseous.
Yeah, exactly.
It's still
pretty
gaseous.
much gas all the way down. And so there would be methane, ammonia, and these other gases being produced in the inside of the planet, the interior, and then they would swell up through convection currents and come up to the upper atmosphere where we could see them. So the fact we see methane is consistent with that picture. We would expect also to see these other things like ammonia. Presently, the current data isn't actually good enough to distinguish that. It is possible it could be one of these worlds, and the amount of ammonia is just below our detection sensitivity.
So it's not a super Earth.
That's a good question. We don't really know what it is.
While observing a relatively nearby exoplanet known as GJ1214b, the James Webb Space Telescope recorded something that startled researchers. Using its advanced spectrographs, Webb peered through the dense atmosphere of the planet and found carbon dioxide levels eerily similar to those in the atmosphere of Venus. This finding didn't align with known planetary categories, which typically slot planets into familiar types: rocky like Earth, gaseous like Jupiter, or icy like Neptune. GJ1214b appears to straddle multiple characteristics. It's more massive than Earth, possibly rocky, yet enveloped in a thick hydrogen-rich and carbon-heavy atmosphere. These traits defied classification, prompting researchers to propose a new planetary class entirely: Super Venus. Unlike traditional super Earths or mini Neptunes, a super Venus is defined by its dense, carbon-laden atmosphere and rocky structure, more akin to our scorching planetary neighbor than any other known world. Researchers, including Everett Schlauwen and Kazumasa Ono, combined Webb spectrographic data with complex planetary formation models to interpret their findings. After rigorous simulations and probability modeling, they concluded that GJ1214b might be the prototype for this new planetary category. While the signals of CO2 were faint and required careful statistical verification, the combination of observed features was strong enough to merit scientific attention. This discovery could change the way we search for habitable planets. While supervenuses are unlikely to host life as we know it due to extreme surface conditions, understanding their makeup helps scientists refine their search criteria. More importantly, it proves that the diversity of planets in this universe is broader than previously thought. GJ1214b, sitting just 48 light-years away, has become a case study in how alien and familiar other worlds might be. The Hubble Tension, cosmic expansion under scrutiny.
Our observations have become so refined that a kind of mismatch has begun to surface between the expansion rate measured directly, right, by looking out in space to relatively nearby objects, and in that way measuring the rate of expansion, versus the expansion rate that we can get by measurements of the early universe and extrapolating those measurements to current times to figure out what the expansion rate should be according to that approach.
That's right, so that the universe we see around us really is hyperdimensional, but we can't see it because these other dimensions are curled up. They're too small to be observed.
Compactification is the word that I think string theorists use.
That's right. If I have a tabletop exists in 2 dimensions, but I can roll it up like in a cigarette, roll it up, and then I see this one-dimensional thing, which is actually 2-dimensional if I get very close with a microscope.
The rate at which the universe is expanding is known as the Hubble rate, denoted with a capital H, and the rate at which it's expanding today is h0. The issue is now that cosmologists have used different measurements to determine this constant h0 and got different results. This is the so-called Hubble tension.
One of the most troubling puzzles in cosmology has been dubbed the Hubble Tension, the discrepancy between the universe's rate of expansion as measured using 2 gold standard methods. The first relies on observations of the cosmic microwave background, using data from missions like ESA's Planck satellite. The second method involves measuring the brightness and pulsation rate of Cepheid variable stars to construct a cosmic distance ladder. The problem? These 2 methods yield vastly different results. Enter the James Webb Space Telescope. Scientists hope that Webb, with its greater sensitivity and sharper resolution, might settle the debate by ruling out measurement errors. Instead, it confirmed the discrepancy. In a study published in the astrophysical journal Letters, researchers led by Adam Rice used both Webb and Hubble to examine over 1,000 Cepheid stars in distant galaxies. The findings were conclusive. The expansion rates are indeed different, depending on which method you use. The implications are staggering. If measurement errors are no longer a valid explanation, then our fundamental understanding of the universe might be flawed. Rice states, quote, "With measurement errors negated, what remains is the real and exciting possibility we have misunderstood the universe." This suggests that the standard model of cosmology, which explains how matter, energy, and time evolved since the Big Bang, may be incomplete or even incorrect in significant ways. Webb's confirmation of the Hubble tension cements it as a genuine scientific crisis, one that may force astronomers to rework theories about dark energy, gravity, or the very shape and structure of space-time. In essence, Webb hasn't solved the mystery, it's made it unavoidable. The crisis isn't just a matter of data interpretation, it's a fundamental crack in the blueprint of the cosmos. Seeing what was invisible to Hubble.
So, this little graphic here is showing the different wavelengths that the famous observational tools are sensitive to. And so, tell us why James Webb was chosen to be sensitive to the particular part of the electromagnetic spectrum that we've highlighted here.
Yeah, so Hubble, which we've been using up until now, of course, is sensitive to optical wavelengths, which our eyes are sensitive to, and a little bit sensitive to the infrared, but James Webb is optimized now for the infrared.
Behind the telescope mirrors is the instrument package, which has the cameras and spectrometers, and we had to invent some things for that too. We needed much better detectors. The detectors are made of 2 flavors, one called mercury cadmium telluride, and one is called arsenic doped silicon. And the combination of those two things give us the sensitivity to the whole wavelength range that we wanted to study.
And that didn't exist before?
Well, they existed, but they weren't good enough. They weren't sensitive enough, and they weren't big enough.
Unlike the Hubble Space Telescope, which observes mostly invisible light, the James Webb Space Telescope operates primarily in the infrared spectrum. This capability allows Webb to peer through thick clouds of cosmic dust and gas that obscure many celestial objects from view. This technological leap has opened up entire regions of space that were previously invisible, revealing phenomena that we had no idea existed. For example, Webb's infrared cameras allowed it to penetrate the dense regions of the Flame Nebula, where traditional optical telescopes saw only darkness. What emerged were not only brown dwarfs, but hints of even smaller, colder, and more mysterious objects. Some of these might be rogue planets, worlds that were formed in planetary systems but were ejected and now drift alone through the galaxy. These are the cosmic loners, unmoored from stars and nearly undetectable until now. Infrared light is also the key to observing the earliest moments of the universe. Because the universe is expanding, light from distant galaxies is red-shifted, meaning its wavelength is stretched into the infrared range. Webb's ability to capture this red-shifted light allows scientists to study galaxies that formed just a few 100 million years after the Big Bang. These observations could eventually lead to insights about how the first stars and galaxies were born. In every direction Webb looks, it's lifting a veil. The instrument doesn't just give us more detail, it opens up entirely new categories of cosmic structures, processes, and relationships. This expanded vision is not just a scientific upgrade, it's a paradigm shift. We're now seeing a universe that was always there, but had been hidden behind curtains of light and time. And what we're finding behind those curtains is challenging everything we thought we knew. Now it's time to hear from you. Do you think the James Webb Space Telescope is uncovering evidence that could change our understanding of the universe? Let us know in the comments section below.